I am Chloe Osborne.
I'm Philip Kalbeck.
I'm Abby Davidson,
And I'm Gretchen Wayhoff.
and we are the Small In-Vessel Composting System. Food waste is a significant issue in the United States, with a staggering 30 to 40% of the 400 billion pounds of food that the U.S. produces ending up in the landfill each year. Composting provides a solution to the food waste problem by utilizing it as a soil supplement rather than throwing it in a landfill to rot. Composting systems are available on the market for large industrial operations and small homes, but our project sponsor, David Neville, saw a need for an affordable, medium scale composting system to be used by small institutions like small farms, schools, and restaurants. The goal of our project is to design and construct a small in vessel composter within a shipping container that is continuous, monitors internal environmental factors, and aerates the compost.
The process of our system goes as follows. To start out, food waste will be input into a hopper on the top of our container via a skid steer or front loader. This includes raw materials such as feedstocks, food waste, wood chips, leaves, and water. Once material is deposited, a temperature sensor will be tracking the temperature of the pile. If the pile is over 160 degrees Fahrenheit, the mixing and aeration cycle will begin for a set amount of time. Otherwise, the compost pile will continue to sit and mature. The temperature sensors will continue to check the pile throughout the system. Once the compost has been sitting for 21 to 30 days, it will then move out of the container via our aerated moving floor system. The floor will meet up with the auger that is lying horizontally to move the mature compost into an external hopper, which is placed outside of the shipping container. Once in the external hopper, the compost is ready to be put into super sacks for storage or use.
Now looking at our 3D model, I'm going to start at the top with the entrance hopper. The entrance hopper is located on the top of the composting bin at a 8 foot by 5 foot entrance, which is large enough for the client to place his skid steer bucket and dump various feedstocks into. It will be covered with a tarp and crank pull system to fit the exact size of the hopper entrance to keep it covered completely when not in use.
As the feedstock enters the vessel, it will be blended and homogenized through the rotating mixing blades. These blades will break up the feedstock material and will facilitate a faster digestion process. This also ensures consistent particle size in the final compost product. The blades will be powered with an electric motor and driven via a torque multiplier attached to the central shaft of each mixing blade assembly.
The sensor system that the client wanted was to have a continuous measuring system with three main data points: temperature, oxygen, and relative humidity. Temperature is important for monitoring as the pile cannot function properly over 160 degrees Fahrenheit. This is important for various reasons in various points of the composting pile. I have one shown in the beginning where the compost enters the system, one in the middle of the process, and one just before it's removed. The oxygen and relative humidity are atmospheric measurements for the whole system, and that is why they're both near the top and next to each other for easy calibration and maintenance access. The oxygen measurement is extremely vital to compost health in making sure there is proper aeration and for a quicker maturation process. Relative humidity relates to the moisture and humidity content in the container, which should be 40 to 60%. Monitoring this in tandem with the temperature and oxygen levels will support the overall health of the system. On the end is the wood chip biofilter. This is the ventilation part of the project that was inspired by one of our compost subject matter experts, Gene Bonhoddle. The wood chips will be acquired from a partnering farm used for this filtration process and changed out once its moisture content gets low. Then these wood chips can be thrown into the pile, bringing full use of this product.
In the bottom of our container, we will have a leachate collection method and aeration. The compost will sit on a raised floor, which is the method chosen for aeration and leachate collection. The compost produces a little bit of liquid called leachate. This liquid is full of nutrients that are great for other plants but can be harmful if it gets into streams or in the environment. In order to make sure that the leachate that comes from the compost pile is safe for our environment, the compost system is designed with that in mind. The floor will be raised about 1.5 feet off the bottom of the container. Within the 1.5 feet, there will be an angled floor to direct leachate to the pump that is located near the exit. There are two angles in the design, one that brings the leachate from the 8-foot width and one that brings the leachate across the 20-foot length. The platform part of the raised floor will be graded with holes about 1/4 inch diameter. These holes will allow for air to be forced through the pile, supplying it with the oxygen necessary to keep the compost alive.
To make our composter continuous, we will implement a graded conveyor floor that moves our compost at a set rate. The compost will move from the beginning of the shipping container to the end within 21 days. The floor is graded to allow air from the fans to reach the compost pile's aerobic bacteria. The conveyor floor will be supplied by IBT conveyors. Because the floor of the composter is graded and we need to ensure that there is enough carbon-rich material, we also have an additional hopper to put wood chips in before the feedstock. This ensures that the compost does not fall through the graded floor and that we will have the right mix of materials.
After moving through the vessel, the finished compost material will be unloaded via spiral augers. The first stage will be installed horizontally across the width of the vessel and will feature an extended input port to auger compost out of the vessel. The second stage will be installed on an incline to auger the compost into an external loadout hopper structure. An oversized transition with a constant velocity joint will serve as the connecting point between the horizontal and incline augers. The external loadout hopper is designed to accommodate the filling of bulk super sacks as well as loader buckets from skid steers or tractors. The beauty of the external loadout hopper is the modularity of it. This component can easily be scaled up or down to meet the specific needs of the user. Some end users of the in-vessel composting system may not require a loadout structure at all, or some users may not need the ability to fill loader or skid steer buckets.
With the complexity of this project, understanding the system and what is happening on a more technical level is crucial. The system is a combination of two different composting techniques, both an aerated static pile and an in-vessel system. With the 8 by 8 by 20-foot shipping container and the equipment that is taking up the system, our maximum composting capacity is 452 cubic feet, also 17 cubic yards. With the capacity that we have, the output volume is going to be 40% of the input volume at about 6.7 cubic yards per cycle. The composting process will take 21 to 30 days with the aeration and speed up the mixing process we have implemented. The primary feedstocks include horse manure, food waste from local schools and restaurants, wood chips, and yard waste. It is important to keep in mind that 20-to-1 carbon-nitrogen ratio. As mentioned above as well, the sensors are vital to monitoring the health of the composting system across the board.
Over the next few weeks, we will begin integrating the electronics and user interface into our system. We will also begin the process of creating the full set of fabrication drawings, the goal of which is to distribute these free to other farmers and institutions interested in pursuing in-vessel composting. Within the mixing system, we will conduct laboratory experiments to determine in-situ blade torque and mixing effectiveness, which will help in optimizing the structural design of the blades. Final steps will involve integrating and fabricating the aeration and leachate collection floors and installing the unloading auger and hopper system.